This mission started as a side quest to make large Lego wheels and tyres that work with Lego. Then I had to figure out how to make tyre moulds. Then I realised I had to make a whole vehicle to drive around to test the new wheels and tyre, and how to turn large wheels with standard Lego cross joints without breaking them, and how to get more power through the Lego model. And so here are my Lego compatible gearbox wheels. There is a 3D model on Bricklink you can download. Please enjoy the video. The 2026 monster truck with gearbox wheels. It's radio controlled with RC servos working the suspension regassing and locking differentials. It has 4 steering modes. The wheels are 3D printed and conical for maximum steering and suspension angles. And these tyres are also 3D printed in thermoplastic polyurethane TPU and have hollow tread. The truck is driving on a 300 watt motor on a 3S LiPo with an FOC controller, allowing full power at low RPM. Here's the 3D printed steering bar under the RC steering servo, which is just a normal standard size servo, although it's digital and metal geared. The gearbox wheels have a 7:1 reduction, 1 large 3D printed bearing and 11 micro metal bearings to fit the Lego axles to hold the planet gears. The Lego air compressors run from the main drive motor from an RC servo clutch. This lets you throttle and control the speed of the suspension. The air switches are between the compressors and the air tanks and air cylinders. So when the switches are closed, the front and rear suspension have their own separate air pressures. Okay, let's see if the Fox is any better at driving. Get that compressor revved up, regassing the suspension, disengage the compressor clutch, and off we go. And the rear lower connecting rods are off already from the previous collision. Maybe we don't have much space on this worktop. And the rear wheels have fallen off the worktop. Good try, Fox. Let's try again with some slow, precision 3-point turns that look calm and intentional. I'm trying different colours of plastic for the wheel bearings to see if there's any difference between the types of plastic, and also variations of the 24-tooth Lego gears I've used as the planet gear in the wheel. Very precise forms, smoothly done. Hit the brakes, Fox. Brakes, Fox. Other brakes, Fox. Not a single Lego Universal joint has been harmed in the making of this video, and the 3D printed sliding axle connectors have also survived. This is the motor mount. It plugs into a printed panel that holds other bearings. Here's the prototype gearbox wheel. It has an 8-tooth pinion and a 56-tooth internal ring gear, giving you a 7-to-1 hub reduction. That means if you spin the Lego cross joints 7 times faster, you can have 7 times more torque at the wheel where you need it. The 3D printed tyres work, but they don't really have the right properties and they're breaking already. The printed purple ring gear, that's also the wheel hub, isn't showing any signs of wear. The transmission in the truck from the motor in first gear to the wheels has a dark grey 16 to 24, then the light grey 24 to 40, then the yellow differential 14 to 22, and then the gearbox wheels 8 to 56, giving you a grand total gear reduction of about 1.5 times 1.67 times 1.57 times 7, which is about 27.5 to 1. The 3D printed differential bearing. It's specialised and asymmetric so the clutch can get into the splines on the differential body. This locks one of the drive axles to the differential body so the truck can climb over stuff and things. Having a look at the purple axle torque tubes and the drop-down gearbox that gets the drive shaft over the steering servo and differential. This steering knuckle design isn't so good. The cross axles pull out with crashes, so I superglued those small Lego parts into the 3D printed wheel hubs. There's a steering servo and printed steering bar. The locking differential uses a printed custom clutch fork in silver to operate the clutch with so little space. And there's the brushless drive motor with its 2 black socket bolts under the anti-roll bar. The tyres are very close to the suspension shocks at full compression on one side. On the next truck, I'm changing the steering knuckles and making the printed torque tubes a few studs longer. The suspension has too much friction. These are standard LEGO pneumatic air cylinders, although I've cleaned out the old pit grease and sliced half the seals off the LEGO plungers that are on the metal rods. They're not free and springy enough yet. The steering servo is standard size and stays between the connecting rods. The drive shaft is just touching the top of the servo with the suspension at full compression. The whole axle assembly stays together with Lego pins and nothing's been glued yet. Here's the power gearbox and the 3 motors I've used. It's the Endura 2204 brushless motor from a small-scale RC crawler. The 2204 means the stator that has the windings wrapped around it is 22mm in diameter and 4mm deep. 2400 kV is how many RPM it will do per volt. Lower kV is less RPM and more torque. I've fitted a 16-tooth Lego gear as the pinion. It's centred on a compression bushing and trapped between the Lego 3L connector and the motor body on a 3mm threaded rod. I pressed the motor shaft out of the motor and replaced it with a machined helicopter linkage with threads with a peak diameter of 2.95mm, which is less than rolled threads. Here's the second motor. It says 2826 on it, but really it's a longer version of the 2204, so it's about a 2210. Top view of the gearbox and compressor crank. That's the servo clutch to engage the blue compressor gears. This one's the 2-speed gearbox with small metal bearings on the Lego axles. I ball race everything now to reduce friction. The black gearbox side panels that hold the bearings are also 3D printed. Here's a close look at the gearbox with the brushless motor. It's really just 2 side panels that hold the bearings and servos. This was my 3rd attempt at the gearbox to fit everything in, and the diameter of the gears limits the maximum diameter of the motor that can be used. This radiant motor can go to 4 cells, or up from 11.1 volts to 14.8 volts. And I'd also have to upgrade the motor controller and the 3-cell ESC. It seemed to be and I'd also have to upgrade the motor controller as it's currently got a 3S ESC, and they seem to be much cheaper than the 4S motor controllers. So what do you think? Let me know in the comments. More voltage first, or a longer and larger motor next? Please comment in the doobly-doo righty space below. the LEGO Technics chassis before refitting the power gearbox. In the middle, there are two black 3D printed triangular lift arms that are 3x7 and made specially to cross-brace the gearbox section of the chassis. These purple pieces are going to be blue on the next truck. There's the gearbox fitted. Good job, Fox. Just got to clip all the Technic clutch pins back in, all at the same time. Here's the suspension kit for the blue truck. I've been making my own plungers out of silicone to see if I can reduce the friction without losing the seal. So I've been incrementally making them at different sizes and experimenting with the edge profiles to make the seals and different types of silicone. And I found I've also had to reinforce them with little plastic plates that slot onto the rods. These are the LEGO parts removed from the air cylinders. Fox loves air tanks, don't you Fox? Blue ones. Let's get an unmodified LEGO pneumatic air cylinder and try moving it to see how much friction it's got. And my modified one goes much faster for about the same force. To get inside the air cylinders, I go under the edge of the black part with a clay modelling tool, then walk the tool around until it's under the dark grey clip. Then lever it away while using the extended rod to also lever the cylinder apart. There's the standard LEGO plunger and stopper. Now let's do the same again to my modified one. So the tool goes in, walk it around and lever the rod out. And here's my custom plunger. And I had to reinforce it with 3D printed plates that slot onto the rod. I tried different types of silicone. I thought I got one set perfect with zero friction. Then I found out the silicone shrank and I had no seal. I also gave them pure silicone oil. LEGO or ABS plastic seems to like silicone, but not Teflon. Netting up a standard cylinder to see its response with air pressure. It seems to go about that fast, and that spring rate might be okay for a very heavy model between 5 and 10 kilograms. With the modified cylinder, the spring or return rate is much faster. My truck is about 3 kilograms, so this looks promising. I've been experimenting with wheels and tyres. The blue truck is getting silver gearbox wheels and silicone moulded tyres. I'm not going to 300 watts per wheel just yet. The gearbox wheels are handling about 75 watts each right now. Here's a rigid 3D printed tyre in hard engineering plastic just to check the initial shape. This one is a moulded silicone tyre made from a 3D printed mould. The tyre wall is not compressible enough, the whole tyre is too heavy and solid. I made an infill in TPU and over-moulded the silicone tyre. The result was too heavy and solid. I put grooves in the infill for the silicone to grab. Only too much silicone went into the infill, and I only got 3/4 of a tyre. It's far too rigid, and the silicone doesn't even bond to the infill that well. Almost no compressibility on the tyre wall, and it weighs a ton. Now this tyre is directly 3D printed in TPU 80A, like the tyres on the truck. I'd say they're low grip and too rigid, but almost okay indoors with 3 wall loops at 300 watts. Here's what's inside a 3D printed tyre. It's just an infill pattern. TPU is literally 3D printable rubber, just it's very stringy, and I don't find the adhesion between the layer lines to be good enough. I am wrecking this one, just to show you. It's very satisfying. And here's the original inspiration for the entire project. Can I use a giant tyre on the LEGO model? This one's a factory no brand in silicone rubber. It's got bolted split rims and a 110 stator motor, which is about 300 watts. It's a high impedance gimbal motor, The blue thing that landed from outer space is my first tyre mould. This is the filler top. Silicone goes in the round holes, and air comes out the triangular holes. Here comes the big unboxing, my second silicone tyre. Inside the mould is very smooth and almost clean since the last use. My new tyre is very flexible and will need a separate infill. I can control that a bit with the tyre wall thickness. The treads are nice and flexible to grip around things, but I have to design it without any breaks in the bead. Inside the tyre, there's a shiny strip where the silicone was in contact with sellotape. The mould tread came out perfectly. Even the flash line was nice. They are extremely low bounce, so the next blue monster truck can get very squashy, high quality tyres. The fitted 3D printed tyres with hollow treads are okay enough, but they're starting to split along the layer lines, and they do this funny thing where the tread gets stuck and pops out later. My Lego monster trucks deserve very squishy, low bounce tyres. Let's have one last look at the gearbox wheels before we let Foxy destroy them. Good Fox. Always give your Fox goggles. In the next video, we're building a blue monster truck and have to spray paint a few pieces, so we're trying a few preparation techniques. Come on, Foxy. Fox brush. Always remember to shake your fox with the